Ever wondered why an apple falls straight down? Let a Eurostrade S uncover the invisible force that pulls everything toward Earth. Gravity is a fundamental interaction that draws objects toward one another whenever mass is present. In everyday life, the most familiar example is an apple falling from a tree because Earth's mass pulls it downward. This pull can be represented by vectors that point from the apple toward the center of the planet. The magnitude of each vector depends on both masses involved and the distance separating them. Newton described this relationship with his law of universal gravitation, which states that every particle attracts every other particle. According to the equation F equals gm1 asterisk m2/r2, the force grows with mass, but shrinks rapidly as distance increases. The constant g is a measured value that links the abstract mathematical description to real-world measurements. When an apple detaches from its stem, the only significant external force acting on it is Earth's gravity. Because no other forces counteract this pull, the apple accelerates toward the ground at roughly 9.8 meters per second squared. This acceleration remains constant for all objects in free fall near Earth, regardless of their mass or composition. Pause 0.8. Newtonian Eurostrade S law states that every pair of masses attracts one another with a force. The magnitude of this attraction is given by F equals g times m1 times m2 divided by r squared. Here, g is the universal gravitational constant, a fixed number that sets the strength of gravity in our universe. m1 and m2 represent the masses of the two objects. Larger masses produce stronger pulls. R denotes the distance between the centers of those masses. As r grows, the force drops sharply, because the denominator is squared. Doubling the separation reduces the force to 1/4 of its original value. This inverse Euro-square relationship explains why objects far from Earth feel a weaker tug than those close by. In our visual, two spheres illustrate Earth and a falling object, while a dynamic bar shows r changing over time. As the bar shortens, the calculated force increases, making the object accelerate toward the larger sphere. Thus, gravity is not a mysterious pull but a predictable interaction governed by mass and distance. Pause 0.8. Newtonian Eurostrade S law states that the force on an object equals its mass times acceleration. F equals ma circumflex a. Near Earth, a Eurostrade S surface, the only significant external force is gravity pulling toward the planetary Eurostrade S center. The gravitational force between Earth and a small body of mass m is F equals g a circumflex m Earth a circumflex m/r2, where m Earth is Earth's mass. Because the radius r is essentially constant for objects close to the surface, we can treat 1/r2 as a constant factor. Dividing both sides of Newtonian Eurostrade S equation by m gives a equals g a circumflex m Earth/r2, which depends only on Earth a Eurostrade S properties. Substituting Earth's known mass and radius yields a circumflex letter QC6 9.8 m/s2, the familiar acceleration of free fall. This value is called g, and it applies to any object regardless of its own mass. Because g is constant, all falling bodies accelerate at the same rate, producing identical motion trajectories. The apple Eurostrade S velocity therefore increases linearly with time, as shown by the slope in the overlay graph. Thus, the pull of gravity near Earth can be derived directly from Newtonian Eurostrade S law without invoking complex dynamics. Pause 0.8. When a heavy and a light ball are released together in a vacuum, they fall side by side. The only force acting on each is gravity, pulling them toward the chamber floor with equal acceleration. Because gravitational force scales linearly with mass, the heavier ball experiences a larger pull but also has more inertia. Newtonian Eurostrade S second law tells us that acceleration equals force divided by mass. The two factors cancel out, thus both balls reach the floor at exactly the same instant, proving that mass does not influence free Euro's fall speed. This experiment eliminates air resistance, so the observed motion reflects pure gravitational dynamics. The transparent chamber allows observers to see the simultaneous impact without visual distortion. Students can record the event and calculate the common acceleration, which matches Earth a Eurostrade S g value of 9.81 m/s a circumflex 2. By repeating with different masses, learners confirm that the ratio of forces to masses remains constant. The key takeaway is that in a vacuum, all objects accelerate identically under gravity regardless of their weight. Pause 0.8. When a feather and a metal ball are released together, they do not hit the ground simultaneously. The difference arises because air molecules push back against each object in proportion to its surface area and shape. This opposing push is called drag force. It grows with speed but also depends on how much air the body presents. A feather, being light and fluffy, has a large effective area relative to its mass, so drag quickly balances gravity. Consequently, the feather slows down early and reaches terminal velocity a constant speed, where drag equals weight a much sooner than the ball. The metal ball, compact and heavy, presents far less area. Its drag is small compared to its weight, so it accelerates longer before reaching a higher terminal speed. In a wind tunnel, we can visualize airflow around each object. Streamlines show how air hugs the feather Eurostrade's surface, creating a thick layer of resistance. The Bala Eurostrade's streamline shape allows air to pass with fewer eddies, so its drag remains low even at high speeds. Thus, in everyday falls, lighter objects that spread more air fall slower than heavier ones, illustrating how gravity is countered by the medium through which we move. This principle explains why skydivers deploy parachute as to increase surface area and drag until their descent slows to a safe rate. Pause 0.8. When the sun exerts a pull on Earth, it creates a centripetal force that keeps the planet in motion. This force does not act like a straight line but curves Earth's path into an ellipse around the sun. The shape of the orbit is determined by the balance between Eurostrade's inertia and the Sun Eurostrade's gravitational attraction. In a perfect ellipse, the sun sits at one focus, pulling Earth more strongly when it is closer. This variation in distance causes Earth's speed to change, speeding up near perihelion and slowing down near aphelion. The result is a closed loop that repeats every 365 days, the basis of our calendar year. Kepler Eurostrade's first law states that planets move in ellipses with the sun at one focus, confirming this observation. Kepler Eurostrade's second law tells us that Earth sweeps out equal areas in equal times, a consequence of conservation of angular momentum. The third law links the orbital period to the size of the orbit, showing how distance from the sun affects the time it takes to complete one revolution. Thus, the same gravitational pull that makes objects fall on Earth also governs the graceful dance of planets around their star. Pause 0.8. Gravity is an attraction that exists between every pair of masses in the universe. Each object exerts a pull on every other, and this pull does not depend on how heavy it is. The force grows stronger as objects get closer, following an inverse square relationship with distance. Because Earth's mass is enormous, its gravitational field dominates nearby objects, drawing them toward the center. When you release a ball, Earth's gravity accelerates it downward at about 9.5 meters per second squared. The same principle explains why planets orbit the sun and moons circle their planets. Newton formalized this idea with his law of universal gravitation, linking mass, distance, and force. In everyday life, we feel this pull as weight, which is simply gravity acting on our body's mass. Thus, regardless of size, every object experiences the same gravitational tug toward other masses. This fundamental mechanism keeps oceans bound to Earth and governs celestial motion across the cosmos. Pause 0.8. Gravity pulls every mass toward every other mass, independent of its own weight. Newton Eurostrade's law shows that this force depends on the product of masses and inversely on the square of their separation. Near Earth's surface, this results in a constant acceleration of about 9.8 a circumflex m/s a circumflex 2, so all objects fall at the same rate in vacuum. In air, drag slows lighter objects more than heavier ones. Finally, gravity keeps planets in orbit by continuously pulling them toward the sun while they move forward.